Hello and welcome to another video on orbital mechanics. This is another theory video before we get on to some more questions. And this follows on from the perifocal frame that I just did. And this is about Lagrange coefficients. Now the Lagrange coefficients look really complicated in the book, sound really important, but really they're just some numbers that come from a set of equations from reorganizing a bunch of equations to make life easy for us. And what it helps us do, it helps us go from one position in an orbit to another position in an orbit via just knowing a few facts about what we're doing, that being the change in true anomaly and the radius and a few of the other constants that are in there. But to start off with, and it is a bit long-winded, and I've tried to keep it all on one page, and I've probably simplified a few things or skipped a few things in places, but try not to get too concerned. Starting off with the radius and the velocity vectors that we saw in the perifocal frame video, and these are at our initial conditions. And then we have the angular momentum equation that we've seen several times now. And when we cross product those, we get, for initial conditions, we get x naught, y naught derivative minus y naught times x naught derivative. That's just through working out and seeing that that is the magnitude of our angular momentum vector. And if we rearrange R naught to get Q, we see this. And if we and then that's step one there. So we have that Q. We can then take that Q and plug it in here, step two. And we rearrange that with the Q replaced. We get down to this. Well, we rearrange for P. We get down to this. And then when we take P and put it back into this Q and rearrange, we get this. So we have something for Q and we have something for P in terms of our initial radius and our initial velocity. That might look a bit pointless, but if you take those two things and you put them back into our original radius equations and vector velocity equations, not for naught, for any point on the orbit, you get these here. So x upon p, sorry, p's there, and y upon our q there. And when you multiply those out, you get this and this. And when you do it for velocity, you get this and this. And what we do, we just take those equations out and call them f, g, and derivative f and derivative g. This is for radius, this is for the velocity. And then we have these equations as well, which are left behind after replacement. So really just a lot of mumbo jumbo, but that's what you get in the end. And these are useful. And if we take our angular momentum equation, which is R naught cross V naught, and put in these, right? But we're not doing it at naught, we're doing it, this is a constant anyway, so naught is irrelevant. We put these things in here, and we cross multiply them. So that cross multiplied with that gives this. And R naught by R naught is 0. V naught by V naught is 0. So we just then and V naught cross R naught equals minus R naught cross V naught. So when you put all that information in, simplify and factor out, you end up with f times g derivative minus f derivative times g times R naught times V naught. And that is again the angular momentum. So, and angular momentum is constant, so h naught doesn't really mean anything. It's always the same. So it just ends up being h equals f times derivative of g minus f derivative times g equals h. So we know that's not 0. That would be 0 if the if you just got traveling straight towards the planet in a rectilinear orbit or just trajectory, rectilinear trajectory. But we're not. We are in an orbit, so we know that it equals 1. Right, so if we know any 3 of those, we could get the other one. I guess you could say that's useful. But anyway, that's kind of a tangential point. These are the important parts here. And from there, probably wondering what the point is, from there, we have x naught, y naught, x naught derivative, and y naught derivative, and all their non-zero versions, which just drop the 0. And we get those from the perifocal frame video I just did. So have a look at that. We can also say that delta theta equals our desired theta minus our initial theta. Right? And we also know these equations here from previous videos. There's lots of those. And if you take these values here and replace them on all of these values and simplify and use this knowledge here, this equation here, and some, cos rules, you can break it all down into these 4 equations. Once you have these 4 values, you can put them back into here and you can get your radius and your velocity vectors. And it's nice to have the vectors. So these are useful equations, I guess, and they can be used for other things, I think, in the next part of the chapter. But to be honest, I could probably get the radius vector and the velocity vector without any of this. So I'm not entirely sure what value this is going to bring down the line, but I think it helps simplify some, it helps shortcut some stuff if you don't have all the information handy. So it is what it is. And it was definitely worth going over. If you think I've made a mistake, which I probably have, or you've got any questions, which I do have questions, but let me know in the comments. All right, thank you. Goodbye.